So in the last section, we learned about the formation of imines. So how do we form imines? Imines are formed with aldehydes or ketones with a primary amine. Now we're going to see what is the structure of the compound if a secondary amine reacts with carbonyl group. Okay, so here's carbonyl group with a secondary amine. And if you guys remember how we made the imine, basically if you had a carbonyl group and then the primary amine had two hydrogens, and then you can have an alkyl group, and then two hydrogen from the nitrogen and the oxygen formed a water molecule, and then we continue to keep the double bond. Now instead of oxygen you put nitrogen there, and then you have your alkyl group, and we call this as imine by losing a water molecule. That's how the imine formed. Now this is a secondary amine. Okay, so here is your carbonyl group, and then the secondary amine has only one hydrogen and it has two alkyl groups. To form a water molecule we need two hydrogens. So where is the other hydrogen comes? Okay, normally the other hydrogen comes from the compound that the carbonyl group belongs to, not from the nitrogen in this case, not from any of these alkyl groups. Okay, so it's going to come from this carbonyl group. Hydrogen on the alpha carbon, so the carbonyl group, and this is the alpha carbon. Hydrogen on the alpha carbon could be any of those. Since it's a symmetrical molecule, comes the other hydrogen to form the water molecule, something like this. We'll look at the mechanism and you will understand how it happens. So this water molecule. So as a result, a double bond is not going to form between the nitrogen and carbon, because then the nitrogen will end up having 4 bonds that need to carry a positive charge. But if the double bond forms over here, like that, okay, like this, so then nitrogen is also neutral. There are no charges in the molecule. Okay. So again, a secondary amine with the carbonyl group form enamine. Enamine means it has an ene group and an amine group. Enamine, enamine. Okay. Ene is going to be in the compound that the carbonyl group is, and then the amine part coming from the secondary amine. Now let's look at the mechanism and you will understand all these things. Similar to the imine formation, nitrogen lone pair, nucleophilic enough to attack the carbonyl carbon. Double bond, from the double bond, pi bond breaks and generating a negative charge, and we are in acidic medium. And the nitrogen will still carry the hydrogen that it came with. So since nitrogen has 4 bonds, it should carry a positive charge. And then since oxygen got 3 lone pairs with 1 bond, formal charge would be negative. So to make it neutral, it's going to grab a proton from the acidic medium, and it will be protonated and giving you alcohol. And nitrogen still carrying it hydrogen. So the conjugate base of your acid will take the proton, excess proton on nitrogen, and will become neutral. Now you have, there are no charges on this tetrahedral intermediate. It's a neutral tetrahedral intermediate. We can call it as a carbinol amine. Okay, you can see all these steps are reversible. Okay, now at this point you can either protonate nitrogen or you can either protonate oxygen. If the nitrogen protonated, the reaction will go back. But the product what we want is to eliminate the water molecule. So oxygen, we're going to protonate oxygen. Oxygen grab a hydrogen, proton, and now we have a protonated water molecule. Oxygen with 3 bonds will become positively charged. Now that there is a protonated water molecule on the neighboring carbon has a nitrogen with a lone pair. Nitrogen pushes the electron towards the nitrogen carbon bond to form a pi bond and want to release this water molecule by doing that. So now elimination of a water molecule takes place. Okay, so you have a double bond. So the nitrogen with the two alkyl groups and a double bond, nitrogen has 4 bonds, so it should be positive 1. Now the neutral molecule would be the most stable. So how can it become neutral? And there are hydrogens on the neighboring carbon. So the base, conjugate base, take the hydrogen and form a pi bond between these two carbons. So then the pi bond between the carbon and nitrogen opens up, and then the 2 electrons that nitrogen lost gonna get back to it, making nitrogen neutral. And then you form ene and imine in amine. Now in this intermediate earlier, if it was a hydrogen here, if you started with the primary amine, this would be a hydrogen. So easily the base can take this hydrogen if it is a primary amine. And then we form the imine. Since there are no hydrogens, so the hydrogen should be gone from the carbon next to the carbonyl group. Okay. This intermediate cannot lose a proton from nitrogen, so it loses a proton from alpha carbon. Alpha carbon is this. So this is the carbon of interest where we had the carbonyl group. This is alpha. Okay, that is how the enamine formation takes place. Beautiful mechanism, isn't it? And just like the imine, this can also be hydrolyzed by adding acidic water. Acid catalyzed hydrolysis converts the enamine back to the carbonyl compound and the amine. So the nitrogen carbon bond will break here. It will get back its carbonyl group and then the secondary amine. And in this process, nitrogen will end up having a hydrogen on it because now it lost the 2 lone pairs to form a bond with the hydrogen. It's no longer basic, so it cannot go back to the formation of enamine. It's an irreversible reaction. Okay, protonated amine is not a nucleophile, so we have to start it with an open nucleophile like this. Okay, so reductive amination is once you form imine or an enamine, either primary amine or secondary amine with a carbonyl group, the resulting imine or the enamine can be further reduced to make this saturated. Okay, and you can see here sodium cyanoborohydride is another reducing agent, a derivative of sodium borohydride. Remember the sodium borohydride that we used to reduce aldehydes and ketones, sodium borohydride. Now you can see here there are 3 hydrides. So instead of 1 hydride, see, cyanide replaces a hydrogen of sodium borohydride. So now we have NaB. Instead of 4 hydrides, we have 3 and cyano group. Okay, we call it as sodium cyanoborohydride. We use that reagent to reduce the imine or enamine to saturated compounds, meaning this is now a secondary amine and a tertiary amine. Okay, so after you form imine and enamine, primary amine with a carbonyl compound, secondary amine with the carbonyl compound, with the sodium cyanoborohydride can be converted to secondary amine or a tertiary amine. That is called reductive amination. Okay, now we're going to move on to another important category that the aldehydes and the ketones can undergo with water. What is it going to do with water? The reaction of aldehydes and ketones with water. Now this is aldehydo-ketone. So you can add water in the presence of an acid. So the water molecule will add on to the carbonyl carbon. If the water adds here, it will end up being an OH group, and this will also become OH. So the carbon will carry two hydroxyl groups. If you started with the aldehyde, this would remain as an H here. If you started with a ketone, the two groups are going to be alkyl groups. We call this as a gem diol. Gem means, or geminal, gem diol, the two groups on the same carbon. Or we can call it as a hydrate. So we call it hydrate and or a gem diol. And this is the mechanism, lovely mechanism over here. Again, we are in the acidic medium. The first thing, acidic medium, is oxygen is going to get protonated. Now we have created a site, a carbon, because this is positively charged, and this carbon will become more electrophilic. So the water molecule is nucleophilic enough for it to come and attack the carbon. And then the carbon-oxygen pi bond opens up and then releases the positive charge on the oxygen. Okay? And the newly attached water molecule will carry now two hydrogens that came with the oxygen. So another water molecule comes and grab the excess hydrogen, giving the neutral molecule with two hydroxy groups, a gem diol or a hydrate. That's how it happens. Reaction of aldehydes and ketones with alcohols. Now we saw here how it reacts with a water molecule. Alcohol, what's the difference between water and the alcohol? So this is HOH, water. Alcohol also have oxygen, also has a hydrogen. Instead of one hydrogen, now you have a R group. So it has two lone pairs. It also has two lone pairs. Now, similar to water mechanism, with water, alcohol also can do the same thing. Aldehydo-ketone. When you add methanol in the acidic medium, first step would be protonation of the oxygen. Similar to water molecule, oxygen lone pair. So just to remind you, first this will get protonated, right, from that HCl. And then the oxygen lone pair can go and attack this carbon, opens up this. And then you will have a protonated methanol, okay? Protonated methoxy group on the carbon, so the hydrogen will be removed, similar to the water addition, and you will be forming this molecule. So with water we had this, you had an oxygen OH, hydrogen no alkyl group OH, right? Now with the methanol, instead of hydrogen, water, since water has alcohol group, R group, alkyl group, so that would be like that. If you start with methanol, so then this is the molecule. You have a OH and OCH3 group. Now we call this as a hemiacetal. Hemiacetal. So basically you had R carbonyl group, hydrogen O another alkyl group, and with methanol, one methanol group, what happened? So one carbonyl group became OH, and then this became OCH3. So two oxygens. Now we have the carbon, one carbon carrying hydrogen, one carbon carrying hydroxy group, the other carbon carrying a methoxy group. We call this kind of a complex as a hemiacetal. Carbon with an alcohol group and another alkoxy group, oxygen attached to another carbon, hemiacetal. Now what happened when you add another methanol? You add another methanol, second molecule of methanol. So then that, we'll look at the mechanism for this one. And that can also add on to the carbon. That can add on to the carbon, this carbon, and then lose this water molecule and form two methoxy groups. Okay. Now it would look like this. You have an R group, carbon, hydrogen, O, another alkyl group. So you have oxygen, OCH3, OCH3. Do you see the difference of hemiacetal and acetal. So in a hemiacetal, where here these are the original groups that was attached to the carbonyl group, and then you have now two oxygens. One is hydrogen alcohol group, the other one is alkoxy group, OCH3. That is a hemiacetal, half acetal, or you can just consider it as a half acetal. And acetal is carbon with two oxygens attached to it. Both of them has alkyl groups, an acetal. So with the two molecules of methanol forms an acetal group. The reaction with one molecule of alcohol forms a hemiacetal. With the second molecule forms an acetal. Now this is the mechanism for the acetal formation. So this is your ketone, and then first we are doing this reaction in acidic medium. It's going to get protonated, and then the methanol will come and attack the carbonyl carbon. Okay, the nucleophile adds to the carbonyl carbon. Then what happens? This oxygen will become neutral, and the methoxy oxygen, because oxygen has hydrogen and methyl on it, even after you attach it to the carbon, you still have hydrogen and methyl attached to it. So with the oxygen having 3 bonds will be positively charged, the conjugate base will come and grab the hydrogen, releases the positive charge. Right? Now you just form an hemiacetal. Now in order to form an acetal, we need to eliminate this water molecule. You can see all of these steps are reversible, but it can also get protonate this methoxy group. If that happens, then it go back here. We don't want to go that path, so we're going to make this oxygen protonated. Yeah, it says here either the OH or the methoxy group can be protonated. Where once oxygen get protonated from the of the alcohol, it become a protonated water molecule. Now the neighboring carbon has a group where it has a lone pair. The lone pair pushes its electrons to form a pi bond and releases the water molecule. Now you have a carbonyl carbon type of a compound with a positive charge on oxygen. This is called O-alkylated intermediate. Now this intermediate is similar to the previously protonated ketone. Earlier, to begin with, you have added an hydrogen but on oxygen, but now you have a methyl group. Okay, again the same thing happened with another methanol. Lone pair of the oxygen attack the carbonyl carbon, releases the carbon oxygen pi bond, making this oxygen neutral, and now the methoxy group attached to the carbon. Methoxy group is still carrying the hydrogen, conjugate base grabs the proton. Now you have an acetal. In acetal, both oxygens are alkyl groups. Okay, that is the mechanism for the acetal formation. Nice mechanism. Now these acetals can be hydrolyzed to get back to the original ketone that we had. Acid catalyzed hydrolysis converts acetal back to the carbonyl compound and the amine. When you add excess water in the presence of an acid, the methoxy groups will get back to the methanol, and then we will get the ketone back. And these are some of the examples of acetal group and hemiacetal groups. Okay, in our body as well as in the food that we eat. This is from carbohydrate. We eat carbohydrate, we have carbohydrate, right? Plant synthesized carbohydrate, glucose, right? So this is D-glucose, and this is the molecule, D-glucose molecule. There is an aldehyde group here and an alcohol group here. Remember, we had seen the hemiacetal formation with methanol. Alcohol attacks the carbonyl carbon. So similar to that, this oxygen lone pair attacks this carbon and form a hemiacetal linkage. Now in this hemiacetal linkage, the carbon of interest or the carbonyl carbon was this one. So it has a OH group and then oxygen with another alkyl group. That makes this is a hemiacetal linkage. Okay, and then in this starch unit, 3 subunits of starch, you can see here this carbon right there has oxygen connected to alkyl group, oxygen connected to another alkyl group. It is a cyclic structure, but still it is a acetal linkage. Okay, so we find these kind of compounds, these linkages everywhere. Now, sometimes we use cyclic acetals as protecting groups during reactions. Let's say we want to protect this carbonyl group. We don't want it to get destroyed when you are trying to do a reaction. So what you do is you're going to protect it by adding 1,2-ethane-diol. Now remember earlier we had seen how a methoxy group attach by using methanol, and then you added another one, so 2 molecules of methanol. Okay, so this molecule OH represent your alcohols are in the same molecule OH, that is OH, CH2, CH2, OH. It's a cyclic alcohol. Okay, glycol, ethylene glycol, ethane diol. So it's 1,2-ethane diol, or ethylene glycol is the common name. So it's a cyclic alcohol. Alcohol group is in the same compound, 2 alcohol groups, instead of adding 2 different alcohol groups. 1,2-ethane diol. Remember we formed acetal, meaning oxygen connected to methyl, oxygen connected to methyl. Now both of them are connected together. So we can kind of protect this carbonyl group. Okay, and then you can perform another reaction where, like, if you had in the form of carbonyl group, it can be destroyed, but now this is not a carbonyl group anymore, so it will not be destroyed by some reagents. Now after the reaction is been done, if you want, you can add hydrochloric acid and get back to your ketone of interest. Same thing, here's another protecting group, 1,3-propane diol, 1, 2, 3 carbons, 1, and the third position we have diol, 1,3-propane diol. So this can be converted to another protecting group like that, having 3 carbons, 1, 2, 3. Using protecting groups in synthesis. Now let's say we want to synthesize this compound from this. There are 2 carbonyl groups. One is a ketone carbonyl group. The other carbonyl group is ester carbonyl group. And between the ketone and the ester, ketone is more reactive and this is less reactive. But we only want to reduce the ester carbonyl group. Since ketone is very reactive, whichever the reducing agent that we are going to use is also going to reduce carbonyl group, not only this one. So by protecting this first, we should be able to carry out the reaction with a reducing agent where ester will reduce to alcohol, but we should be able to get back the ketone. How can the ester be reduced without reducing the ketone? So you have 2 carbonyl group, 2 functional groups. You add ethylene glycol or 1,2-ethane diol, and this will only react with the carbonyl carbon of the ketone, not this one. Okay, not with the ester carbonyl group. So you're going to be forming a protecting group. Now you can add lithium aluminum hydride. Lithium aluminum hydride is a very strong reducing agent compared to sodium borohydride. Because ester is less active, we need a strong one. When ketone is normally strong, active. So with the lithium aluminum hydride, if you do not protect your carbonyl compound here, both of these will reduce to CH2. Okay, so you protect it, then you do the reaction. So only this part will be reduced to give you CH2O minus. When you add hydrochloric acid and water, oxide will grab a proton and become alcohol, and then we can get back the carbonyl group. Okay, so the formation of acetal is important so we can protect the carbonyl group and do a reaction. Also, OH group can convert to ester to protect. Now let's see here, we have OH group here, we have OH group here. And we only want to react this alcohol group, not the carboxylic OH group. We are going to protect it in the form of a ester. Ester is this functional group. Now when the ester is being formed, when you add alkylating agent like thionyl chloride, this will not react with an ester. Whereas thionyl chloride can react with the carboxylic acid and make this also a chloride group. So how do you make the ester? Acid with, this is a carboxylic acid. Carboxylic acid with the acid catalyst and alcohol, ethanol, in excess can form an ester. We learn the mechanism when we talk about the esters, carboxylic acids and all that. And then thionyl chloride, when you add the thionyl chloride, it's going to replace the hydroxyl group to chloride. If you did not protect this, if you keep it like that and add the thionyl chloride, this hydroxyl group will readily convert to chloride. Now it cannot be done because OH group is protected. And then if you want to do further reactions with this chloride, you can react with another nucleophile like cyanide group. So the cyanide will react with this carbon in the SN2 fashion and leave chloride, and then will attach cyano group. And then if you want to hydrolyze cyanide group to make it an acid, you can do that. If you want to reduce this to amine group, you can do that also. But here we are going to convert this to acid by hydrolyzing the cyano group with acid and water. And during that acidification process, the ester group that we've been protecting here is also going to hydrolyze to the acid back. So you're going to get the two acids back, acidic groups. Okay, that's how we can use to convert an acid to ester to do a reaction when alcohol group needed, alcohol group is also there. Okay. Okay. Let's do these two slides too. The reaction of aldehydes and ketones with thiols. Thiols are also a form of an alcohol, but instead of oxygen, now you have sulfur. Remember, oxygen and sulfur are in the same group. They both are in group 6. So they kind of have similar reactivities. So methanol is CH3OH. Sulfur is right below that. Same group, have the same reactivities, same patterns. So this is methane thiol. So if an alcohol can react with a carbonyl carbon, thiol sulfur can also react with this carbon. And if you add two methanol, remember two groups attach with oxygen, oxygen here and form acetal. Now with the thiol groups, the two thiols can add on to the carbon. We call it as a thioacetal. And thioacetals formation also a very good protecting group. Okay, so here you have a ketone can react with 1,3-propane dithiol, and then you form a thioacetal. If it was two oxygens, 1,3-propane alcohol, 1,3-dipropanol, it would be acetal. Now with the sulfur, we can call it as a thioacetal. And if you want to get back to the ketone, you can do a hydrolysis with acid, but if you want it to be completely desulfurized and get back to the carbons, you can use hydrogen and nickel to reduce that carbonyl group. Okay, so this is a reaction right there. We'll stop here.